Okay, so our next speaker is Brice Halimi on category theory and set theory, algebraic set theory, as an example of their interaction.
First of all, I would like to thank the organizers, particularly Francesca and Andrea, for putting together this great conference. Can you hear me or
not very well?
No, like that. No. Or maybe I will switch to the.
Maybe now. Try.
So I wanted to thank you for putting together.
We heard that.
I can say it twice, 3 times.
Thank you. Now you can switch off the mic.
So is it okay?
Yes.
Yeah. Okay. So my talk will bear on quite technical stuff, and unsure of being able to set it out properly. I would like to emphasize the main thread. So set theory may have a peculiar foundational status, but it constitutes also a branch of mathematics in its own right, and as such it interacts with all the other branches of mathematics. And in my view, there's no linear order where set theory comes first, and then you have less and less foundational mathematical theories. So that would be my first point. And my second point spins off from the previous one. Even if it's usual to reconstruct mathematical objects in set theoretic terms, that does not mean that we should describe them in set theoretic terms. I mean, using set theoretic tools only. And in particular, one can look at set theory from a non-set theoretic point of view. So this sounds very common. Think of topos theory, for example. But algebraic set theory, the theory I will be interested in, is not about replacing ZFC set theory with something else. Algebraic set theory is really about keeping ZFC itself and mixing it with a geometric perspective. A geometric perspective where gluing processes come to the fore. So I will try to explain all that. Okay, so it's not about replacing ZFC, so that's why I will speak of a fruitful combination, interaction between ZFC and a branch of category theory. And I will focus on the first 3 axioms of the original axiomatization of AST by André Joyal and Yeke Moerdijk. So I will argue that AST is a genuine graft of the theory of fiber categories onto ZFC, and that is a way of overcoming the unfruitful rivalry between set theory and category theory. So the original motivation is that, in fact, championing set theory or category theory is just extrapolating a tradition within mathematics. And in general, it's not about foundations. In a way, foundations are provided neither by set theory nor by category theory. So it's not about that. So I think it's better to leave foundations aside and to try to go beyond the context between set theory and category theory. And I think that algebraic set theory does the job. So there are 2 different approaches to algebraic set theory. A logical one has been preferred by Steve Audi in particular, and a geometrical one by Joyal and Moerdijk. So I will be interested in the latter, in the Joyal-Moerdijk presentation only. So in that presentation, we start with a Heiting pretopos C. So a Heiting pretopos is just a category C, rich enough to interpret first-order logic and arithmetic. But C is not supposed to be a topos. In particular, it's not supposed to have power objects. So now, the basic idea, the starting point of Joyal and Moerdijk is to characterize a special subcollection of the collection of all maps of C, a class S of so-called small maps in C. Intuitively, an arrow is a small map if all its fibers have a set-like size. So instead of thinking of sets, we think of arrows. And an object, X of C, is said to be small if the canonical map from X to the terminal object of C is a small arrow. So, and then you obtain a characterization of sets, namely small objects. But there is a detour through small maps, and small maps are the target of algebraic set theory. So, of course, it suits category theory. Arrows are brought to the fore instead of sets, and sets themselves are conceived of as fibers. I will explain. So here are the axioms, the first axioms for the class S of small maps in Royal-Murdoch book. So I will be interested only in the three. So maybe I could get rid of that cross. Okay. So any isomorphism of C belongs to S, and S is closed under composition. So this axiom corresponds to the fact that there is a union of a small, that the union of a small family of small sets is a small set. When I say small set, I mean small object.
Sorry.
So a set in the algebraic set theory reconstruction of sets. Now the second axiom is stability under change phase. So if you have a pullback like that, if F belongs to S, so if S is a small map, the pullback of F, G, is also a small map. And the third axiom is called descent, and Royal-Murdoch don't say anything about that. Book is very dense and terse, so there's no explanation. For any pullback along an epimorphism P, if G belongs to S, G is a small map, then so does F. So is F. Okay, so I will get back to the notion of pullback, but it's a quite general notion, basic notion of category theory. And of course, I did not mention that, but I suppose that you know that a category is a collection of objects endowed with a collection of maps between these objects, and that's all that you need to know. Okay, and just for the sake of completeness, we have all other axioms. So you have spatial arrows from the initial object to the terminal object, and from the sum of the disjoint union of the two copies of the terminal set object to the terminal object. So those two arrows are supposed to belong to S, and this axiom ensures that the empty set, the initial object of C, is small, and that any finite set is small. The second condition ensures that any finite set is small. Okay, so you have other axioms, and I won't linger, I won't dwell on those. So now, just to show you that you can catch up with ZFC. If you consider a partially ordered set, post-set in C, then the set of maps from any object A to L is itself a post-set. So that's a classical result. And then Murdoch and Royal define what they call the supremum of a map lambda along another map G. So it's a map mu here, such that you have that very complex condition. So I won't explain. It's a very intricate thing, but it's a way of rendering the notion of supremum in a classical post set. Now, a post set L is said to be as complete if any map to L has a supremum along any map in S. Recall that S is the collection of small maps that is the target of the theory. Okay, now you can define a ZF algebra in C. It's an S-complete poset, L, with all joints, endowed with a map S. So, what does it mean? The partial order of the poset L corresponds to inclusion, and the map S corresponds to the singleton operation. And so, if you're given a ZF algebra LS, you can define a membership relation. You will say that in L, X belongs to Y if and only if the singleton of X is included in Y. Okay, so you can mimic the membership relation in the framework of algebraic set theory. Now, you can define the notion of homomorphism of ZF algebras in C is readily available. And then from that, you can define the free ZF algebra generated by any object A of C. And there's a result in the book that free ZF algebra always exists. Okay. And in fact, that free ZF algebra is the generalized cumulative hierarchy on A. And now you have that result. You have to throw in two further assumptions on, about the class S. But you have that A plus the free ZF algebra generated by A is a model of ZF set theory with atoms. So A plus means the disjunct union. So you really get ZFC model. Now, the main purpose of my talk is to explain the elliptic phrase descent used to describe the third axiom of algebraic set theory. Just to get, yeah, this one. So descent theory is a central tool of abstract algebraic geometry, coming from Grothendieck work. And descent theory makes sense only in the general framework of fiber categories or fibrations. The two terms are synonyms. So I will explain what fibrations are, what descent consists in, and then what is the explanation of the first three axioms of algebraic set theory. Okay, so I will give you the flavor of it. I won't, of course, explain everything, so sorry if I am a bit quick. So a fibration is a functor P from one category F to another category C, okay? And the idea is that it's a functor that is a generalization of the notion of surjective map in set theory. So it's a kind of surjective functor. And if you take, if you take an object X of C, the pre-image of X, P minus 1 of X, is a category written F sub X and called the fiber above X. So it's just the category theoretic version of the set theoretic notion of pre-image. That's all. And the main point, the main thing that is added with the fibrations is that if you have an arrow in the base category C, that arrow will give rise to base change functors between the corresponding fibers. So here is the picture, and you don't need to keep anything else in mind. So you have a functor F, P from F to C. C is the base, and for each object of the base you have a fiber, the pre-image. And the main thing is, if you have an arrow, a map, here from X prime to X in C, that induces a functor, a U star, between the fiber above X to the fiber above X prime. That's the main ingredient compared to surjective maps. Okay, so here is an example. You take the continuous functions, all the continuous functions, and all the topological spaces. If you have a continuous function, you consider its domain. So if you have a function f from u to x, you consider that function have u as a domain, and so u is its image by the functor by the domain function. So above you, the fiber above you is composed of all the arrows with U as domain. And if you have a map from V to U, you can readily define a functor from the set of all maps with U as domain to the set of all maps with V as domain. The definition of the functor is just composition. F as U for domain, F U will have V for domain. Okay. So now, given category C, you consider the category of all arrows in C. There is a basic example of a fibration. The codomain functor is a fibration. So you have C as the base category, and above C you have all the arrows. And each arrow will be sent to its codomain. And that defines a fibration. Now, I think that the motivation of, the main idea behind the first axioms of algebraic set theory is that the class S of small maps is conceived of as a sub-fibration of this codomain fibration. So you have, in fact, to think of the class S of small maps as a big category above the category C, and the fiber above each object of C is composed of all the small maps having that object for codomain. Okay, now let's get to descent theory. Descent theory is an abstract framework here to describe gluing processes. That is the shift from local data to a global item. It's something pervasive throughout geometry. You could define it in a way, geometry as the theory of gluing processes. So here is a typical example. Imagine you have a space U and a covering of that space by open subsets UI, U sub I. And suppose that you have a continuous function from U sub I to V for each I. And on top of that, suppose that those functions are compatible when they overlap. That means that on the intersection UI, how do you say that? Pronounce the symbol?
J?
I mean, this one.
The intersections.
Intersections? Okay, so you consider the intersection U sub I intersect U sub J, and the functions are agreed on that intersection. So you have a function on each subset of the covering, and the functions agree together when they overlap. Then there exists a unique function f from the total space U to V, whose restriction to each U sub I is the function f sub I. So you can glue all the function f sub I to get a global function f. That's the basic example, and what many geometrical theories are interested in. So you can reformulate that in the context of the fibration that I've shown a few slides earlier. So if you write U prime as the disjunct union of all the subsets U sub I, you have a canonical map from U prime to U. And in fact, the family of f sub I is an object in the fiber above U prime. Now you can introduce the pullback, double pullback of U prime. So what does it mean? That means that what you get, U prime times U prime, is in fact a way of representing the disjunct union of all the intersections. Now, if you have a family of functions, f sub I, in the fiber above U prime, the image by the base change functor P1 star is the family that you get when you restrict all the functions fi to the intersection U sub ij. And same thing for the pullback along the second projection, P sub 2. So the hypothesis about the family of functions was that they were compatible, that they agree on their intersection. I mean, on the intersection when they overlap, where they overlap. So a way of rephrasing that the functions agree together, is to say that the pullback of the family along P1 and the pullback of the family along P2 are identical. That's just an abstract way of rephrasing the systematic agreement of all functions. Okay. So here how it works. You have U prime. U prime is just the disjunct union of all the U sub i's, and the pullback U prime times U prime is just the family of all the intersections. And above U prime times U prime, you have all the restrictions of the f of the functions to use I intersection uj, and they agree, which means that in the fiber above U prime times U prime, you have that equality. Now you can replace, and that's how it works, you replace identity with an isomorphism. And so you want that all the pullbacks to be isomorphic, not necessarily identical. That's a kind of generalization. And if you have that, you can glue the local data above the components ui of the cover in U prime, so as to get a global item above U, which is the space covered by the covering. So descent theory is about formalizing that process of gluing local data to get a global item. So I will be quick now. I mean, not quick, but I won't delve into the details. I want just you to have that idea of functions that agree on when they overlap, and so that you can get a global function out of the family of local functions. That's the main idea. So Grothendieck in 1959 introduced the notion of descent theory. I mean, of descent, and he formalized everything in a very general way. So in the context of any fibration. So what I showed you is about the specific fibration of continuous functions above topological spaces. So here is just the generalization to any fibration. So you have a fibration F above a base category C. Recall that each time you have an arrow in the base category, you have a base change functor in the other direction. Now, Grothendieck defines what he calls a descent datum on C prime. C prime being an object in the fiber above X prime. What is it? It's an isomorphism between the two pullbacks of X prime, exactly like in the example that I have just set out. So you want that the restrictions of C prime agree. And when you have an isomorphism that witnesses for that agreement, you say that you have a descent datum on the object C prime taken in the fiber above X prime. Now, having defined a descent datum on an object, Grothendieck defines what he calls a descent morphism. F descent morphism, F being the fibration under consideration. So you forget about that slide, of course. But what does it mean for alpha to be a descent morphism. That means that what should glue actually glues along alpha. So here is a more telling picture of what is going on. So you want two things. Suppose that you have an arrow V in the fiber above X prime in such a way that the two images of V by the two base change functors, P1 star and P2 star, are identical. If we have such a V, we want that V defines a global item, U. And that's what we want. The first condition for alpha to be a descent morphism is that if V satisfies P1 star V equals P2 star V, then V comes from a global item U. V is then the localization, if you want, of U. That means that we can find a global item U that is the result of gluing the data encoded by V. So the fact that V is alpha star of U means that V can glue, the components of V can glue so as to define a global item U. And the second condition is exactly the same thing, but about objects, not about arrows. So suppose that you have an object psi prime above X prime, and you suppose that the two pullbacks, the two images of psi prime by the two base change functors, P1 star and P2 star, are isomorphic, exactly like in the example we considered. If we have such a situation, then the components encoded by psi prime can be glued together so as to give an object C above X. So if each time we have an item psi prime that satisfies the condition that its two base change images are isomorphic, then we can glue the data encoded by psi prime so as to get a global item psi and along alpha. The fact that we can glue the data encoded by psi prime to get a global item psi along alpha is expressed by that condition. Okay, so sorry for that. Now I'm finished. You suffered, but now it's over. The basic result that Grothendieck obtained, and that is the first result of descent theory, is that if you consider the codomain fibration, a descent morphism is exactly the same thing as an epimorphism in C. An epimorphism is a surjective map. So Grothendieck identified all the descent morphisms as being exactly all the epimorphisms of C. So now we can rephrase, reconstruct, or reinterpret the first three axioms of algebraic set theory. Any epimorphism in C is a strict descent morphism for the subfibration defined by the class S of small mass of the codomain fibration. And so, in fact, we have that result that is not in the book that we can reconstruct. A subcategory S of a subcollection of maps satisfies the first three axioms of algebraic set theory if and only if the fibration that it defines satisfies Grothendieck's property. So here is the reinterpretation of the first three axioms of algebraic set theory. Axiom 1 says that all isomorphisms in C belong to S, which implies that for any object of C, the identity belongs to the fiber above A. so that there is at least one object above each object of C. So the fibration defined by S is not empty. Axiom 2 says that any pullback of any arrow in S belongs itself to S, which ensures that the restriction to S of the codomain fibration is itself a fibration. So in fact, the class S of small maps actually defines a fibration, which is a sub-fibration of the codomain fibration. Now, axiom 3 finally says that Grothendieck's results about the codomain fibration remains true about the fibration defined by the class S of small maps. So a class of small maps, in the sense of algebraic set theory, can be partially characterized as a category to which descent theory applies. So of course, if there are further work, but to ahead, but my conclusion is just that final slide. From a set theoretic point of view, any map is in fact a set. There is no arrow in set theory. Function is a set. On the contrary, algebraic set theory reinterprets set theory so as to turn it into an arrow-based theory along the codomain fibration, rather than an object-based theory. Of course, it's typical of category theory. Typical category theory thinks in terms of arrows and not in terms of objects. But there is more, and that's what I wanted to show. In fact, algebraic set theory represents the graft of the theory of fibrations onto ZFC. In fact, algebraic set theory can be seen as the categorical implementation of ZFC with a deep geometric twist. I think that it is an example, a nice example of combination between foundational mathematics and mathematical practice. Thank you.
So thanks loads. I think it's really good that people are seeing this battle between set theory and category theory as totally unfruitful and trying to merge the two in a nice way. I had one question about a particular example you get in set theory, which is that it's often said that set theory gets the notion of isomorphism on partial orders wrong. So you define a partial order as you define a isomorphism as a bijective homomorphism in set theory, and then you get these partial orders that are bijective and homomorphic, but intuitively not isomorphic. Now here you've got the category theoretic definition gets this, broadly speaking, right? So here you've got a sort of fusion between the two theories, and I'm just wondering how these sort of pathologies play out in the context of your theory. So do you get a nice setting where you can make these distinctions more clear, and rather than just appealing to the intuitive notion of isomorphism, you actually get a precise formal explication of what's going on?
Sorry, I'm not sure I understand completely. Is your question about partial orders or about isomorphisms?
Both isomorphisms. I mean, it's just generally how do these sort of pathologies you get in set theory, what the category theorists tell me so how does your...
Yes, you get these pathologies in set theory where it appears to get the notion a little bit wrong, and you have to place ad hoc restrictions on things. So, I mean, how does this behave in these sort of pathologies behave in your framework?
I'm not sure I'm able to answer. I mean, isomorphisms are defined in a very classical way in category theory. It's just the most natural way, the definition is the most natural one. It's just a direct generalization of isomorphisms in a set theoretic framework. I think that, so I don't think that category theory has much to say about isomorphisms compared to set theory. But what is true is that isomorphisms in the framework I've just set out, and more generally maybe in category theory, an isomorphism is always the indication that an arbitrary choice should be made but can be disregarded. Like, okay, if we make another choice, since we work up to isomorphism, it does not change anything. So it's a way of neutralizing arbitrary choices. So that's why there are always isomorphisms, conditions, isomorphisms and isomorphism conditions in particular in this theory, because we don't want to be dependent on an arbitrary choice that we've made in the process. So that's the main idea there.
Mathematical practice and history of mathematics are full of results of the interpretation of the theory within another theory. But generally a result like that is important if there is some sort of advantage in the interpretation. It can be a mathematical advantage, it can be a philosophical advantage, it can be an epistemic advantage. It depends on the situation. So here you suggest, if I understand well, begin by an interpretation of set theory that I've seen by algebraic set theory, and then you show that, I did not quite understand, perhaps, that at least partially algebraic set theories are interpreted in the center theory, the three axioms. I did not grasp the three axioms, all the axioms that are other that are not interpreted, but you will explain. So at least there is a partial interpretation of algebraic set theory within the center theory. So the question is, you think they are simply a result from the point that show that the ZIC is not unique for foundation, so simply a pluralistic view of foundation. Look, you can let instead of that, which is already a philosophical point, or you see something more there. That is a true interpretation as some essential advantage, either a mathematical one or perhaps an epistemic or philosophical one.
Okay, so I think that the main advantage of algebraic set theory is generalization. So that's why I wasted some time showing you the result that that one. Okay. We have a kind of generalization of set theory. We have new ways of building up models of set theory. So it's a kind of generalization. Now, descent theory is built into the axioms only as far as the first three axioms go. I disregard the other ones, which don't have to do with descent theory. Now, the advantage, I don't know yet. I mean, there's a technical advantage in the generalization itself. They get other results, and the logical program launched by Audi also got results. So it's but it's true that Audi program don't take care. Doesn't involve the descent theory thing. I think that the descent theory ingredient is in the original axiomatization by Joyer, not in the Audi version. Now, I think that the main interesting point is that we have a dramatic shortcut between set theory and abstract algebraic geometry. You think set theory being foundational and algebraic geometry being one of the last, leaves of the mathematical tree. And in fact, there is a brutal, stunning crossover between the two. So that's I think it's interesting. And I think that there are very deep geometric intuitions to be added to set theory. So, and I think it's so I cannot answer yet what it could give. I mean, from a technical point of view or even from a philosophical point of view. But I think that the set theory lends itself to implementing geometric intuitions, which are technically very powerful. So I think that's in itself interesting.
So you can give...
Sorry.
Sorry.
Very quick. Very quick.
Very good question, maybe in the same vein of Marcos. So, if I understand well, you use the descendant theory to give a motivation, an explanation of the axiom of algebraic set theory.
The first three ones, yeah.
Exactly. So, you are talking about set theory developing an algebraic and geometrical intuition, but can you reverse this? In the sense that what you get from the set theoretical intuition, knowing that three of the axioms that you have to develop set theory in the context of category theory has this motivation coming from the descendant theory. So what you get in the set theoretical side, coming back from the category theory side.
I think that what you get is replacing set theory in a more general framework, the framework of five versions, which is in fact much more general than, it's maybe the most general framework used by mathematicians. I mean,
It's not a purely...
So you plunge set theory in that framework, and of course you can try, so it's experimental work, you can try to apply to algebraic set theory all the results that you have in descent theory. So I don't know which ones will apply, to what extent it will apply, but there is some hope, I guess.
Okay, so we thank again.